matrix mechanics. Other representations of quantum mechanics soon followed, for example, the wave mechanics driven by the Schrödinger equation, and Paul Dirac's notation representing evolution in a space of quantum states. These became better known than matrix mechanics, but the underlying philosophy of the Heisenberg representation was not forgotten. In fact, the great Niels Bohr passionately advocated it, insisting that what matters are the observables, the measurable start and end points of an experiment. According to this philosophy, the unobservable details that happen in between are not only irrelevant, it may be meaningless to even talk about those details as real physical events. Despite its importance in the foundation of quantum mechanics and being championed by Bohr and Heisenberg, most physicists over the following decades did not subscribe to this philosophy, at least not in practice. They remained reductionists, and the quest continued for a detailed mechanical description of the hidden inner workings of atoms and the universe. This search for the underlying clockwork of reality led to quantum field theory, in which all particles are described by vibrations in elementary fields that fill the universe, and all interactions are calculated by adding up the exchanges of infinite numbers of virtual particles. But one ignores the wisdom of Heisenberg and Bohr at great peril. Early quantum theory was plagued by problems. For example, how do you compute infinite interactions? And how do you avoid the infinite interaction strengths produced by some of those infinite sums? Some clever hacks, perturbation theory and renormalization, worked in many cases to tame the infinities and yielded the incredibly accurate predictions of quantum electrodynamics, which describes the interactions of the electromagnetic field. But problems returned when we started to peer into the atomic nucleus. At the beginning of the 1960s, the atom was understood as fuzzy quantum electron orbitals surrounding a nucleus of protons and neutrons. Those nuclear particles were originally thought to be elementary, so to have no internal structure, just like the electron. But new experiments were revealing that they seemed to have some real size, as though they were made of yet smaller particles. These were scattering experiments. Particles were shot into atomic nuclei, and the internal structure was probed by the way those or other particles emerged. Such experiments revealed that the forces binding these subnuclear particles together must be so strong that space and time should break down at those scales, and even our best field theory hacks seemed to fail. And so, a number of physicists turned back to Heisenberg's old idea. What if it were possible to understand a scattering experiment, like those used to probe the atomic nucleus, not by modelling all the cogs and wheels of the field theory of the internal nucleus, but rather by understanding the observables only? In this case, the observables were the particles that entered and left the nucleus in a scattering experiment. In fact, Heisenberg himself was way ahead of the game. He'd already laid the groundwork in the early 40s with his work on something called the scattering matrix, or S-matrix. The S-matrix is a map of the probabilities of all possible outgoing particles, or outstates, for a given set of colliding particles, or instates. The idea was invented by John Archibald Wheeler in the late 30s as a convenient way to express the possible results of a quantum interaction. In fact, it's still a very important tool in quantum mechanics today, but Heisenberg took it in a very different direction. In standard use, the S-matrix can be calculated if you understand the forces in the interaction region, for example in the nucleus of an atom. But what if you don't know those internal interaction forces? Heisenberg sought a way to ignore that internal structure and rather treat the S-matrix itself as fundamental. The S-matrix was to become the physics of the interaction rather than an emergent property of more fundamental internal physics. Heisenberg made some progress in the 40s, but the approach came into its own 20 years later when the atomic nucleus refused to give up its mysteries. Through the 60s and 70s, Geoffrey Chew and others took Heisenberg's work on the S-matrix and his anti-reductionist philosophy and developed S-matrix theory. At the time, nuclear scattering experiments were producing a startling variety of different particles. For example, many different mesons were discovered, which we now know to be composed of two elementary quarks. But at the time, prior to the discovery of quarks, no point-like elementary nuclear particles were known. Rather than searching for smaller and smaller particles, Chu and collaborators promoted a nuclear democracy in which no nuclear particle is more elementary than any other. They attempted to build scattering matrices with no elementary particles at all, and with no details of nuclear structure. But how is this even possible? Remember that quantum field theory fastidiously adds together a complete set of virtual interactions that contribute to the real interaction. S-matrix theory sought to avoid this, and instead tries to model a scattering experiment to build an S-matrix by applying some general consistency conditions and then looking for the only scattering results consistent with those conditions. These conditions include things like conservation of energy and momentum, the behavior of quantum properties like spin, and the assumption of a family of particles that can be involved in the interaction. But in order to avoid those sums of Feynman diagrams, S-matrix theory also relies on symmetries between those virtual interactions. In particular, something called crossing symmetry. An example of this is the fact that antimatter can be treated as matter travelling backwards in time. That folds together large sets of Feynman diagrams and helps us to ignore the actual causal structure within the interaction region. And here's another example of crossing symmetry. Imagine two particles scattering off each other. Two go in, two go out. The out particles could be different to the in particles, or they could be the same, just with different momenta. There are two broad ways this can happen, as follows. 1. The ingoing particles exchange a virtual particle, which deflects or transforms them into the outgoing particles. This is called the S-channel. Or 2. The particles annihilate each other, briefly forming a virtual particle, which then creates the two outgoing particles. That's the T-channel. In regular quantum field theory, you'd need to add up all the different versions of both of these two channels separately. Before quarks and their interactions were properly understood, doing that sum seemed impossible in the case of strong force interactions. But in 1968, Italian physicist Gabriele Veneziano figured out a hack. It had been postulated that the S-channel and the T-channel should lead to identical scattering amplitudes. That fact enabled Veneziano to ignore the fiddly details of the separate channels and derive a scattering matrix, which in turn allowed him to explain the peculiar relationship between the mass and the spin of the mesons. The S-matrix approach to solving problems in quantum mechanics, based on these global consistency conditions and taking advantage of symmetries, is also called a bootstrap model, from the expression pull yourself up by the bootstraps, the idea of raising yourself up without a concrete starting point to push off of. So S-matrix theory looked extremely promising until it didn't. It presented severe challenges on par with those plaguing quantum field theory, and as it happened, physicists solved the QFT challenges first. Breakthroughs in our understanding of the behavior of quarks and gluons revealed that the strong nuclear force does not actually approach infinite strength, as was once feared. And so, a full quantum field theoretic description of the strong nuclear force was possible after all. The result is quantum chromodynamics, our modern description of subnuclear physics. QCD deserves its own episode, so I'll skip the details for now. But the result was that S-matrix theory was sidelined and quantum field theory reigns supreme to this day as our reductionist description of the subatomic world. So, do we really now have a perfect mechanical description of the smaller scales of reality? Well, not so fast. Standard quantum chromodynamics employs sums over large numbers of intermediate virtual states, and as we discussed in our episodes on virtual particles, the physicalness of these states are questionable at best. Quantum field theories like QCD surely give us insights into the nature of the fundamental workings of the universe. Given their astounding predictive success, by comparison, S-matrix theory now seems less fundamental. It seems like an emergent set of relationships, what we call an effective theory. But it turns out that it has led to deep insights that even quantum field theories could not reach. So I said that S-matrix theory got sidelined. That's not exactly true. Remember that clever bit of work by Gabriele Veneziano? It turned out that the Veneziano amplitude for meson scattering represents something rather more profound than just predicting the results of a scattering experiment. Other physicists quickly realized that it was telling us that mesons could be described by a very particular type of physical system, a vibrating string. And so, string theory was born, at first as a description of strong nuclear force interactions before quantum chromodynamics took over, but then as a theory of quantum gravity. So our leading and possibly only current contender for a theory of everything was first derived as a bootstrap model, an S-matrix theory. Oh, and another example of bootstrapping a scattering interaction without understanding the internal physics? Stephen Hawking's derivation of Hawking radiation. And physicists are bringing the S-matrix back. Here's an especially awesome example. We think of the largest structures in the universe today, galaxies and galaxy clusters, as collapsed from quantum fluctuations in the extremely early universe. Those fluctuations sometimes caused by individual particles. Princeton's Nima Akani Hamed and collaborators have performed what they call a cosmological bootstrap to understand the nature of those early subatomic scale interactions based only on current observations, which in this case is the distribution of gigantic galaxies on the sky. Well, that's a cool result. But Akani Hamed's work on something called the amplitudahedron has hinted that the S-matrix approach can be taken much, much further. The amplitudahedron takes Heisenberg's old philosophy to the extreme. Only consider the observables. The amplitudahedron doesn't just eliminate the fiddly mechanics of quantum field theory, it removes the very concepts of space and time. These only emerge later as consequences of spaceless, timeless particle scattering. But all of these new efforts deserve their own episodes. Then we'll see how a simple insight by a young scientist in 1925 allowed us to pull ourselves up by the bootstraps towards a better understanding of the quantum weirdness of space-time. Before we jump to your questions, I just want to mention that the best and fastest way to get smart people answering your questions is to join the Space-Time Discord channel. It's hopping with lively conversations about everything space physics or things that spacey physicsy people are into. The Discord is open to anyone who joins us on Patreon, even at the lowest $2 a month tier. Okay, so previously we talked about a compelling new idea for how black holes might merge. Perhaps they're captured and then brought together in the searing hot accretion disks of quasars. Persona non grata asks whether migration traps are like Lagrange points. Well, not really. In fact, we covered Lagrange points last week. Migration traps are different. If you place any massive body in an accretion disk, it will both tug on and be tugged by the surrounding gas. In some places, it gives up angular momentum, its orbital energy, to the gas, causing it to migrate inwards, while in other places, it steals angular momentum, migrating outwards. And between these inward and outward migration regions are places where no angular momentum is exchanged and, well, the black hole is trapped. Adam Wolg asks whether the gas surrounding a pair of merging black holes might significantly affect the gravitational wave signature. Well, the answer is that those waves would be affected, but not by much. Gas causes the black holes to merge faster, so that should increase the frequency of those waves, and to a lesser extent, the actual shape of those waves. But the fact is, almost all gas is going to be ejected from the near region of these merging black holes before they actually collide, and LIGO only sees the merger in the last second, so the effect would be weak. LIGO is unlikely to have the sensitivity to distinguish a gassy from a non-gassy merger for any individual merger. It may be easier with neutron star mergers, which we see a LIGO signal of up to a minute before the merger. Q suggests that it's oxymoronic to say that all you need is a little quasar to catch black holes, suggesting that there's no such thing as a little quasar. Well, actually that's not quite true. Active galactic nuclei come in many sizes. Quasar is the name we use for the largest and most powerful, where you can actually see the accretion disk. Full-blown quasars are powered by supermassive black holes, a few tens of millions to 10 billion times the mass of the Sun. And the small end of that range is indeed a little compared to the insane top end. And below the quasar range, we have weaker active nuclei,